Welcome to this walkthrough of LeetCode problem number 2113, elements in array after removing and replacing elements. In this video, we will break down the problem statement, explore the approaches to solve it, and analyze the complexity. Stay tuned as we dive into the details and learn valuable techniques for tackling similar challenges. The problem requires us to work with an integer array called nums, which contains n distinct elements. Along with this array, we are given an integer k that specifies the number of operations we need to perform. In each operation, we remove one element from the array and replace it with a new integer that is not already present in the array. After performing exactly k such operations, we need to compute the total number of distinct elements in the array. The output will be a single integer representing this total. For input, we are given the array nums as a list of integers, and k as the number of operations to perform. The output will be the total distinct count after all operations are complete. To better understand the problem, let's look at an example. Suppose we have nums equals 1, 2, 3, and k equals 2. Initially, the array contains three distinct elements, 1, 2, and 3. In the first operation, we remove any one of these elements, say 1, and replace it with a new distinct integer that is not already in the array, such as 4. This changes the array to 2, 3, 4. In the second operation, we remove another element, for example 2, and replace it with another new distinct integer, such as 5. This changes the array to 3, 4, 5. After performing the two operations, the array now contains 5 distinct elements, 1, 2, 3, 4, and 5. The output for this example is therefore 5. Now let's examine a second example. If nums equals 1, 2, 3, 4, and k equals 4, the array initially contains 4 distinct elements, 1, 2, 3, and 4. In the first operation, we remove an element, such as 1, and replace it with a new distinct element, like 5. At this point, the array becomes 2, 3, 4, 5. For the second operation, we remove another element, say 2, and replace it with a distinct element, such as 6, resulting in 3, 4, 5, 6. Continuing with the same example, we perform two more operations. In the third operation, we remove another element, such as 3, and replace it with a new element, like 7. This updates the array to 4, 5, 6, 7. Finally, in the fourth operation, we remove an element, such as 4, and replace it with a distinct element, such as 8. The array becomes 5, 6, 7, 8. After performing all four operations, the array contains the distinct elements 5, 6, 7, 8. The total number of distinct elements is therefore 8. For another example, if nums equals 10, 20, 30, and k equals 0, no operations are performed, so the array remains unchanged. The total number of distinct elements in this case is simply 3. Now let's consider the constraints and edge cases for this problem. The size of the array nums can be as small as 1 and as large as 10 to the power of 5. Each element in nums is guaranteed to be distinct and has a value between 1 and 10 to the power of 9. Additionally, the number of operations k can range from 0 to 10 to the power of 5. Some important edge cases to consider include situations where the input size is at its minimum, such as when nums contains only one element and k equals 0. Here, the output is simply the size of nums. Another case is when no operations are performed, meaning k equals 0, and the array remains unchanged. We also need to handle cases where k is larger than the initial size of the array, ensuring we account for all possible replacements. Finally, for maximum constraints, the solution must be efficient enough to handle nums and k both at their upper limits of 10 to the power of 5. To tackle LeetCode problem number 2113, we first need to consider different approaches to handle the removal and replacement operations efficiently. The brute force approach is the most intuitive starting point. Here, for each of the k operations, we manually identify the element to be removed, replace it if necessary, and repeat the process until all operations are complete. While this method is straightforward, it involves iterating through the array repeatedly, which results in a time complexity of O, k*n, where n represents the size of the array and k is the number of operations. This makes the brute force approach impractical for larger inputs, as the repetitive iterations become computationally expensive, slowing down the solution significantly. Alternatively, a balanced binary search tree, such as Java's treeset, maintains the order of elements while supporting efficient insertions and deletions. To address the inefficiencies of the brute force method, we can leverage optimized data structures. The key idea is to dynamically manage the state of the array during the K operations, enabling faster removal and replacement of elements. For example, a min heap or max heap allows quick access to the smallest or largest elements, making removal and updates more efficient. Hash maps can also be utilized to track element frequencies, simplifying updates and searches. With these data structures, each operation has a time complexity of O log n, leading to an overall complexity of O k * log n. This is a significant improvement compared to the brute force approach, especially for larger inputs. Another option is to use sorting, where the array is initially sorted to streamline operations. However, sorting has its drawbacks, as it requires an initial cost of O n log n, and may not handle continuous updates efficiently when k is large relative to n. After evaluating the different approaches, we selected the optimized method using data structures such as heaps or balanced binary search trees. This approach stands out due to its logarithmic time complexity per operation, making it highly scalable for large input sizes. Dynamic data structures provide the flexibility to handle insertions, deletions, and replacements efficiently without the need for repetitive reprocessing of the entire array. While the brute force method is simple to implement, its inefficiency for large inputs makes it less practical. Similarly, while sorting the array initially can simplify certain cases, it falls short when frequent updates are required. The breakthrough realization here was understanding that leveraging dynamic data structures allows us to maintain both efficiency and adaptability during the operations, making it the best choice for this problem. Each approach we considered comes with its own set of trade-offs. The brute force method is straightforward but suffers from poor scalability due to its O k * n complexity. Sorting can be useful when the problem involves static or partially dynamic operations, but it struggles with continuous updates, limiting its effectiveness in this case. The optimized approach using data structures strikes the right balance between performance and flexibility. While its implementation may be more complex, the resulting efficiency, especially for larger values of n and k, makes it the most suitable solution. Ultimately, the optimized approach provides the best trade-off between computational complexity and problem requirements, ensuring a scalable and practical solution for handling the given operations. To begin, let's break down the problem at hand. In this challenge, we are given an array, nums, and a series of operations that either remove or replace elements in the array. The goal is to efficiently determine the final state of the array after applying these operations. Each operation is defined as a tuple consisting of a type either remove or replace, an index indicating where the operation is to be performed, and, in the case of a replace operation, a value to update the element with. Now, before we proceed, there are some important edge cases to consider. For instance, if the array is empty, remove operations are irrelevant and should be skipped. Similarly, if an operation's index is outside the array's bounds, it should be ignored to prevent errors. With this understanding of the problem and its constraints, let's outline the steps of the algorithm. The next step is to iterate through the list of operations and process each one systematically. For a remove operation, we first check if the given index is valid, that is, it falls within the bounds of the current array size. If it is valid, we remove the element at that index using the pop method. However, keep in mind that this operation has a time complexity of O n, since the removal causes elements to shift in memory. For a replace operation, we verify the index's validity again, and if it's within bounds, we simply update the element at that index to the specified value. This is a much faster operation with a time complexity of O(1). Once all operations are processed, the final state of the array is returned. By breaking the problem into these manageable steps, we ensure the algorithm is both clear and adaptable to handle any input that fits the problem's definition. Now, let's highlight some key insights about the algorithm. First, while replace operations are efficient with a time complexity of O(1), remove operations are more costly, requiring O(n), due to the need to shift elements after a removal. This means that the overall time complexity of the algorithm is O k * n, where k is the number of remove operations, and n is the average size of the array during those operations. It's also worth noting how the algorithm handles edge cases. For example, operations with invalid indices are gracefully ignored, ensuring they don't disrupt the process. Similarly, an empty array remains unaffected by remove operations, as there's nothing to remove. By carefully managing these scenarios, the algorithm is robust and capable of handling a mix of operation types seamlessly. The choice of data structures plays a critical role in the implementation. The input array, nums, is a dynamic array, which allows for straightforward removal and replacement of elements. This matches the problem's requirements well. The operations are stored as a list of tuples, providing an easy way to sequentially process each one. However, there are potential optimizations to consider. For instance, if the problem allows, reordering operations to perform all remove actions first can significantly reduce the number of shifts in the array. Alternatively, if the array is large and operations are frequent, using a linked list instead of a dynamic array could make remove operations much faster, reducing their complexity to 1. On the other hand, replacing elements in a linked list would become more costly. These trade-offs highlight how the choice of data structure impacts the algorithm's performance. Finally, let's analyze the algorithm's complexity in detail. The time complexity is k*n, where k represents the number of operations and n is the average size of the array during removal operations. This is because remove operations dominate the performance due to their n cost. The space complexity, on the other hand, is 1, as all operations are performed in place on the input array without requiring additional storage. To solidify our understanding, let's walk through an example. Consider the input array nums equals 1, 2, 3, 4, and the operations remove, 2, null, replace, 1, 5. Initially, the array is 1, 2, 3, 4. During the first operation, we remove the element at index 2, resulting in 1, 2, 4. During the second operation, we replace the element at index 1 with the value 5, giving us the final array 1, 5, 4. The output, therefore, is 1, 5, 4. This example illustrates the algorithm in action and its ability to handle both operation types efficiently. This Python implementation solves the problem by iterating through the list of operations and applying them sequentially to the input list, nums. The method elements after operations accepts the array nums and a list of operations. Each operation is represented as a list where the first element specifies the operation type, either remove or replace. For remove operations, the specified index is validated to ensure it is within bounds of the array. If valid, the element at that index is removed using the pop method, which adjusts the array dynamically. For replace operations, the method validates the target index and assigns the new value to the specified position if the index is valid. The algorithm processes each operation in sequence, modifying the array in place. Finally, the modified array is returned as the result. This approach ensures that all operations are applied correctly while handling edge cases such as invalid indices gracefully. The solution is efficient, with a time complexity proportional to the number of operations and the size of the array. Here, we begin with the definition of the elements after operations method, which takes two parameters, a list of integers called nums and a list of operations represented as lists of objects. The goal is to either remove or replace elements in the nums list based on the operations provided. We start by iterating through each operation in the operations list. For each operation, we extract the operation type using operation.get0, which is expected to be a string, such as remove or replace. If the operation type is remove, we retrieve the index to be removed using operation.get1 and ensure it is within the bounds of the list before calling nums.removeIndex. Similarly, if the operation type is replace, we retrieve the index to replace and the new value from the operation, again checking that the index is valid. If it is, we update the corresponding element in the nums list using nums.setIndex, new value. Finally, after processing all operations, the modified nums list is returned. Now, in the main method, we see an example of how this solution can be used. We first create an instance of the solution class and initialize a list of integers, nums, with values from 1 to 5. Next, we define a list of operations, where the first operation removes the element at index 2, and the second operation replaces the element at index 1 with the value 10. These operations are passed, along with the nums list, to the elements after operations method. The result, which is a modified version of the nums list, is then printed to the console. As expected, the output here shows 1, 10, 4, 5, reflecting the removal of the element at index 2 and the replacement of the value at index 1. This demonstrates how the method processes each operation sequentially to transform the list accordingly. In this example, we start with an array nums containing the elements 1, 2, 3, 4, 5. We are given a single operation, remove, with the parameter 2. First, we establish the initial state of the array and the operations list. Now, we process the given operation. The remove operation targets index 2, so we check if the index 2 lies within the valid range of the array indices, which is between 0 and len, nums, 1. Since the index is valid, we proceed to remove the element at index 2, which is the value 3. After removing this element, the array is updated to 1, 2, 4, 5. This final state of the array is the output for this example. Here, we are working with an array nums initialized as 10, 20, 30, 40, 50, and a sequence of two operations, remove at index 1 and replace at index 2 with the value 99. First, we review the initial state, which includes both the array and the operations to be performed. Then, we process the first operation. The remove operation targets index 1, so we check if it falls within the valid range. Since it does, we remove the element at index 1, which is the value 20. This updates the array to 10, 30, 40, 50. The updated state of the array after this operation is noted, and we move on to the second operation. Next, we handle the second operation, which is a replace operation. It specifies replacing the element at index 2 with the value 99. First, we check if the index 2 is within the valid range of the array indices. Since it is valid, we replace the element at index 2, which is the value 40, with the new value 99. After performing this operation, the array is updated to 10, 30, 99, 50. With all operations completed, the final state of the array is 10, 30, 99, 50. Now, let's consider another example where some operations involve invalid indices. In this example, the array nums starts as 7, 8, 9, and we have three operations to process: remove at index 3, replace at index -1 with 100, and replace at index 1 with 15. First, we process the remove operation at index 3. Since the index is out of bounds for the array, this operation is skipped, and the array remains unchanged as 7, 8, 9. Next, we handle the replace operation at index -1 with the value 100. Again, the index is invalid, so this operation is skipped, leaving the array unchanged. Finally, we process the replace operation at index 1 with the value 15. The index 1 is valid, so the element at index 1, which is 8, is replaced with 15. The array is now updated to 7, 15, 9. The final output of this example is the updated array 7, 15, 9. Here, we analyze the time complexity of the given code. First, for the remove operation, which uses nums.pop of IDX, the time complexity depends on the position of the element being removed. If the index is at the end of the array, the operation is O1, because no shifting of elements is needed. However, in the general case where the index is not at the end, all subsequent elements in the array must be shifted to the left, making the operation O(n), where n is the current length of the array. On the other hand, the replace operation, nums, IDX, equals new_val, involves directly updating the value at a specific index. Since no elements are shifted or resized, this operation runs in constant time, O1. Next, let's consider the complexity of iterating through the operations. If there are m operations in the operations list, we process each operation one by one. Checking whether an operation is a remove or replace is an O1 operation. For a remove operation, the time complexity of nums.pop_idx is O(n), as explained earlier. For a replace operation, the complexity is O1. Now, looking at the overall time complexity, if all operations are remove, the total cost involves summing the lengths of the array as it decreases with each pop, n plus n1 plus n2 plus 1, which evaluates to O(n squared). In contrast, if all operations are replace, the total cost is O(m), since each replace takes constant time. On average, the complexity depends on the mix of operations, but a high number of remove operations will dominate, leading to a worst-case time complexity of n squared. Now, analyzing space complexity, we start with the input data. The nums array and the operations list are provided as inputs, so their space requirements are O, N, and O, M, respectively. Beyond the input data, the algorithm performs in-place modifications on nums, meaning no additional arrays or data structures are created. This ensures that the algorithm does not use extra memory for storage. Additionally, temporary variables such as LPIDX and new_val are used during the iteration to hold intermediate values. These require only O1 space, which is negligible compared to the input sizes. To summarize the overall space complexity, the algorithm operates directly on the input data without creating new data structures, resulting in an auxiliary space complexity of O1. When we compare this to a brute force approach, which might involve creating a new array to store the intermediate results after each operation, the brute force method would require O(n plus m) space, where m is the number of operations. However, the current solution is more space efficient due to its in-place modifications. In terms of time complexity, the algorithm still faces a worst case of O(n squared due to the cost of remove operations. While the best case, where all operations are replaced, achieves O(m), the time complexity bottleneck remains inherent to the use of POP with Python's array-based lists. Overall, the algorithm strikes a good balance by minimizing space usage, but the time complexity is dominated by the overhead of remove operations in the worst case. When working on this problem, it's essential to be mindful of common mistakes. For instance, ignoring edge cases such as empty arrays, arrays with a single element, or arrays where all elements are identical can lead to runtime errors or incorrect results. These edge cases are crucial because they test the robustness of your solution, and overlooking them might cause failures in real-world scenarios. Another common pitfall is relying on inefficient brute force methods, like nested loops, which can result in high time complexity, often O(n squared, or worse. This approach becomes impractical for large input sizes, such as when n exceeds 10,000. Misunderstanding the problem statement is another frequent issue. For example, not clarifying whether elements are removed permanently or only temporarily, or how replacements affect future iterations, can lead to implementing incorrect logic. Lastly, off-by-one errors, such as miscalculating indices or mishandling loop boundaries, can cause array index out-of-bound errors or logical inconsistencies. Being aware of these pitfalls is the first step toward writing a robust and efficient solution. Additionally, it's important to consider time-space trade-offs when solving this problem. For example, overusing auxiliary data structures like stacks or hash maps may seem convenient but could lead to exceeding memory limits for large inputs. While these structures can simplify logic, their memory overhead must be accounted for. On the bright side, recognizing patterns in array modification problems can make a big difference. Techniques like two-pointer strategies, sliding windows, or prefix and postfix sums frequently appear in similar challenges. Spotting these patterns can significantly reduce the time spent devising a solution. It's also essential to clarify requirements upfront, make sure you fully understand the problem statement, constraints, and how modifications should affect the array. Optimization is another critical area to focus on. Interviewers often prioritize clean, efficient solutions over brute force, so aiming for O(n) or O(n log n) complexity is ideal. Finally, debugging step by step using small test cases is a great practice to catch logical errors early. Simulating your algorithm manually can help ensure it works as intended. To deepen your understanding, it can be helpful to explore related problems that share similar concepts. For example, LeetCode 26, remove duplicates from sorted array, involves modifying an array in place to maintain order while removing duplicates. Similarly, LeetCode 283, move zeros, requires shifting elements while preserving relative order. LeetCode 27, remove element, is another great example, where you remove specific elements from an array while minimizing the use of extra space. Lastly, LeetCode 977, squares of a sorted array, focuses on transforming and sorting arrays efficiently. All of these problems emphasize operations like in-place modifications, maintaining order, and optimizing time and space complexity. Practicing these will not only enhance your problem-solving skills but also prepare you for variations of this challenge. Now, let's discuss some alternative approaches that can be applied to this problem. The two-pointer technique is especially useful for in-place modifications since it allows you to process the array efficiently without additional memory. However, implementing it can be tricky, especially when the problem involves multiple conditions to consider. Another option is the greedy approach, where you make decisions at each step to achieve a globally optimal result. While this method is powerful, it doesn't always guarantee the best solution, so knowing when to apply it is crucial. Auxiliary data structures like stacks, queues, or hash maps can also be helpful for storing and manipulating intermediate results. The trade-off here is that they require additional space, which might not be feasible in memory-constrained environments. Lastly, sorting-based solutions are effective when order matters, as pre-processing the array can simplify the logic. However, sorting introduces O(n) log n complexity, which may be unnecessary if the problem can be solved in O(n). Understanding these approaches and their trade-offs will enable you to choose the most suitable method for the problem at hand. Thank you for watching this walkthrough of LeetCode problem number 2113. Today, we reviewed an efficient approach to process and modify arrays based on specific conditions. Remember to practice similar problems to reinforce your skills. If you found this helpful, please like, subscribe, and share with others. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!